Multiple predictors. What happens when one explanatory variable isn't enough? In simple regression, we used a single x to predict y, but in reality, many factors influence the outcome. Multiple regression lets us include several explanatory variables, x1, x2, and so on, all in the same model. This gives us a more complete picture and lets us adjust for confounders. The population multiple regression model says the expected y, given the x values, equals alpha plus beta 1 times x1 plus beta 2 times x2, and so on for k predictors. We estimate this with the sample equation. Y hat equals b0 plus b1 x1 plus b2 x2, and so on. The standard error of the regression now divides by n minus k minus 1, where k is the number of predictors. The key to understanding multiple regression is interpreting each coefficient while holding other variables constant. Here's a real example from a childhood respiratory health study. FEV, forced expiratory volume, is predicted by smoking status and age. The smoke coefficient is negative 0.209, meaning smokers have 0.209 lower FEV on average after adjusting for age. The age coefficient is positive 0.231, meaning each additional year of age is associated with 0.231 higher FEV after adjusting for smoking status. The crucial phrase is holding other variables constant. Here's a stunning example of why multiple regression matters. In a simple regression of FEV on smoke, the coefficient was positive 0.711, suggesting smokers had higher lung function. How can that be? The answer is confounding. Older children were more likely to smoke, and older children naturally have higher FEV due to larger lungs. Age was confounding the relationship. When we add age into the model, the coefficient for smoke flips to negative 0.209. After adjusting for age, smoking does reduce lung function, as expected. Let's think about this geometrically. With one predictor, we fit a line in two-dimensional space. With two predictors, we fit a plane in three-dimensional space. With k predictors, we fit a surface in k+1 dimensions, which we can no longer visualize, but the math still works. What about categorical variables? We can include them using dummy variables. For example, Smoke 2 has 3 levels: non-smoker, former smoker, and current smoker. For k categories, we create k-1 dummy variables, each coded as 0 or 1. Non-smoker is the reference category, coded 00. Former smoker gets a 1 for D1, and current smoker gets a 1 for D2. Let's summarize. Multiple regression includes several predictors in one model. Each coefficient is a partial slope, interpreted while holding other variables constant. This lets us adjust for confounders, as we saw with the smoking and FEV example, and categorical variables can be included using dummy variable coding.